what we are going to see here is basically this indigenous 5G network architecture which we had recently designed, okay, and this is one of the first 5G network to come out of academia, and we'll discuss that, how it was designed, and it is primarily based on whatever we have understood till now in the class, okay. Of course, you need certain things which are like required to make the system complete, okay, but the architecture part we can like try to comprehend from our learnings till now, okay. So this is what we are going to see, okay. So ideas which we have learned will help us in designing this or understanding this 5G network, okay, design, and then I think we'll have some time, so we'll start discussing this PDCCH chain also, okay, physical downlink control chain, okay. So let's see that, okay. Again, we are back to what we understand very well till now, okay. We understand this part of it, RF also. Our complete, what is this? This is the baseband chain, right, okay. So transfer block gets mapped onto a two-dimensional grid finally, okay. Then it gets converted to the time domain, gets up converted, right, okay, at the transmitter side, down converted, then gets sampled, then this is time domain signal, CP gets removed, take the FFT, you form the two-dimensional grid, then do the reverse processing, right. Now this is what we have understood, this is the physical layer part of it, okay. Now, but the system is not only formed by a physical layer, and I have told you that there are multiple other layers which are required for the system to work, okay, right. And what were those layers? I am just recapturing that so that it becomes easier for us to understand why networks are architected in a particular way, okay. And our focus is on the network side, which is the base station, okay. Similar ideas are applicable for the UE side also, okay, right. So what is the first layer? Service data adaptation protocol, okay, quality of service management. Some applications will require one kind of service, another application will require another kind of service, okay. So that's what this layer does, okay. Then there is this packet data convergence protocol layer, PDCP. Encryption, it does a lot of other things, all these layers do a lot of other things, okay, but I am latching on to what we understand so that you know the importance of these layers, okay. So don't get carried away by this fact that I have mentioned only one aspect of it. There are 1,000 other things which these layers will do, okay. Radio link control, segmentation, concatenation, duplicate detection. A huge file gets segmented into multiple data blocks. Then duplicate detection is basically ARQ, wherein we understand that certain data packets due to error can get duplicated also, okay. Then MAC, this is what we understand very well now, okay, that basically where, how many users should be scheduled in a slot, and it's 100 megahertz of bandwidth with 275 PRBs, okay, where in this huge bandwidth each user should be scheduled, right, how many PRBs should be allocated, okay, right. We have discussed 3 different schedulers to decide that, okay, and whose task is that? This is MAC, okay. Most of the decision making is done in this layer, okay. Then it implements hybrid ARQ also, okay, right. And then this is our favorite. As a communication engineer, of course, there are people who do it like who have to do it, and they understand it very well, okay, right. So this is what we have understood till now. Physical layer, coding on transmitter, decoding at the receiver, modulation, demodulation, okay. We have not touched upon this, it will come later, okay, but it does all these tasks, fine, okay. So these are different layers which have to sit. Base station is designed using this, correct, okay, right. And this, all this is software, correct, and you should have a hardware which should execute this, correct, like a computer which has to execute all your instructions, okay. And then look at the difference in the functionality of each of this layer or the philosophy, okay. Look at this MAC, what is it doing? One of the tasks, deciding. It has to make lot of decisions. There's certain kind of processors which are good in doing this, they are bad in doing this. What is happening here, okay, no decisions. All the decisions are told to you, please take this much data, process it, okay, and this has to be like how much fast it should be done. Okay, it should be done. The entire processing has to be done. Okay, within a duration of a slot, 0.5 millisecond. Right? You cannot overshoot that. Okay, because if you are overshooting it at the base station, then system is not stable. Okay, because the next set of data is going to come. Then if you have still not done with this, then what will happen to that data? Right? So very strict time constraints over here. Okay, right? So this decision can be made in advance. Okay, if that this user should be scheduled unless until it's some high priority user like URLC. Right? So this is the difference. These are the differences in like the requirement, processing requirement of each of this layer. Right? And other thing is like the base station, the cellular system have basically the centralized architecture wherein base station makes all the decisions. Okay, that's what, and UE does not have any capability to make any decision. Okay, where at what time it has to send its data, in which PRPs it has to send its data. All those decisions also are made by the base station, and MAC does it. Look at the complexity of doing it. So it is responsible not only for transmitting downlink data, it is responsible for scheduling user also in the uplink and where it should be scheduled, at what time it should be scheduled. Okay, so base station is the boss. Okay, right? UE does not have any freedom in deciding anything. So, and this is what we have seen. Right? I'm just bringing it back. So there are these multiple users. Okay, so each user has like data for downlink here, of course. Okay, right? This is the data which is sitting in buffers for which needs to be transmitted. Where is it sitting? Let's say in the MAC layer, right? Similarly for other users, correct? And this data needs to be transmitted on air, and that's what we are doing. Right, so this is a base station, and each user has a different time frequency varying channel. Okay, channel for each user changes over each PRP or multiple PRPs, right? And in slots also. Okay, so basically, base station has to decide all of that which user should be transmitted based on this information. Okay, and a similar decision has to be done for the uplink also. When should this user be scheduled? In which part of the slot? Okay, right? So the same decisions have to be made for the uplink as well as for the downlink. Okay, so and see this, as I said, we have seen this picture earlier also. What is this? This is a channel. Okay, of let's say I'm showing for 2 users. Here, one channel is like better because you can see this yellow color. Okay, blue is hiding behind it, under it. Okay. Here, user 2 channel is better, blue one has come up. Okay, so what is it showing underneath? This is 2-dimensional grid. Okay, this is some old figure, so it is, don't get carried away by this. This is, these numbers are, right? So what is happening here? Okay, user 1 channel is, this user channel is better here. This yellow is when the user 1 channel is better. Blue is user 2 channel is better over these PRPs at this time. Right, so this is, users need to be fitted in this 2-dimensional grid, correct? Okay, and who is making all these decisions? As I said, MAC layer. And what physical layer gets it? What did we see? That, okay, you have done this processing, then map onto these PRPs. Finally, physical layer has been told everything to do. But who is the brain? The scheduler. Okay, and a lot of decision making, as I said, I'm reinforcing on this fact, a lot of decision making has to be done. Okay, right? So this is downlink scheduling, uplink scheduling also use the same principle. Okay. Now, keeping this in mind, okay, how do we architect a base station or a G node B? And that's how you'll see that this is exactly gets translated into the hardware design, into the software design. Okay, right? So we'll see that again. We come back to this. So what is coming to us here is MAC has already decided where the users are going to be scheduled and send its data and the control information. Okay, we understand both of this very well. Okay, physical layer has to do all these tasks. Correct? Okay. Now, so what is this? This is a software architecture. Okay, right? That these. Okay, so I'll have to go back too much in time. So what is this? There are layers sitting up. Okay, they also need to get executed, right? Okay, MAC, then there are like RRC, everything is there. Okay, and then physical layer. How do you design a system by considering the peculiar data processing requirement each of this layer has, right? And that's what I'm going to show you, okay? We'll go through this same thing, whatever we have seen till now, okay? So what is this? Application data, multiple SDAP, PDCP, RLC, MAC, okay? These layers in 5G jargon put together, they are called L2, L3, right? And after this, what do you get? This is our MAC5 interface, LDPC coding, scrambling, modulation, layer mapping. After that also, I have not taught you here is what is layer mapping, what is beamforming, okay, this is MIMO processing. But we have seen this, resource element mapping, OFDM, DAC, ADC, RF upconversion, antenna, okay. I have not connected antenna, but antenna is there to radiate the signal. Right, this is what is happening, right? Okay, there is an entire software which needs to get executed. Application goes through all of this, right? Fine. Okay, I am still not spoken about what is this hi-fi, low-fi, BBU, RLH, okay, right? But this is the entire, look at the software, this is how your complete processing is happening. This we'll see later, okay, we'll get back to it, but this is part of the chain, MIMO, okay, right? So this is what is it, this is complete physical layer, this is L2, L3 stack. Lot of decision making here, lot of brute force processing here. Okay, so devices which are good in doing this are basically typically 8086 microprocessor. Okay, write your C code, write a lot of if else statements, get done with it, right? So you basically use this kind of processing. Okay, use like servers with high processing power. Okay, right? Once you do this, then give the data along with the control information to some other device which is good in doing this. Okay, and what are these devices? Typically FPGAs or DSPs. Okay, right? So those are the devices which will do this processing. Okay, complete processing also. Okay, right? Now, so this processing is typically done by FPGAs, okay, or DSPs. Now commonly FPGAs. Okay. This processing is done by 8086 servers. Okay. Fine. So you have decided now, you know that, okay, I need 8086 server, I need FPGAs for this, right? Okay. This is physical layer. Now, what is happening here is, and this is where 5G is different from 4G, okay, there is this additional split which is sitting here, okay. You see this, I am calling this as hi-fi, I am calling this as low-fi, okay, because this is lowest to the RF, I mean, this is closest to the RF as soon as the signal comes, okay. So the lowest, bottommost part of the transceiver chain. Okay. So what is happening here? So this processing again is done by FPGAs, okay, but is split from this. Okay. We'll see why. Okay. But briefly, okay, what happens is like when you do this, okay, all this processing can get done in one place. Okay. Right. So you can basically have servers for this, design some daughter cards which can do this processing, okay, right. So what you do here is basically form a cloud data center, you can do that, okay, right. Basically put all this processing at a common place, okay, and run these servers, okay, right. And then basically after this, what is this? This is which is close to the RF, okay, then take this signal through some connection and do this processing close to the antennas, okay. And you look at this, this is basically all your baseband signal still, right. Till 4G what was happening, this was also part of this same chain, okay. Then this signal was being fed to antenna, there are a lot of losses here. So take the RF signal out and then you have to run a long cable, then there will be a lot of losses there, okay. The digital signal, no loss, okay. You can transmit as like in form of optical signals. One reason. Now, there are some companies who are good in doing this, there are some companies who are good in designing this, okay. Flatten the market, wherein give chance to these companies also, so that they can do it, right. So increase the competition, that will bring down the cost. That is one of the main reasons for coming out with this kind of architecture. We'll see, okay. That's how it is architected also. So what is this? So till here, this is called hi-fi. All of this get implemented in something called the baseband unit, okay. other one gets implemented in the remote radio head. So there are companies who do only the baseband, there are companies who do only the radio. Okay, fine. So people, and then you have to connect that. Ideally, it should work. Okay, right, over an common optical link. It should work. Fine. Okay, that's why typically it is done to create market opportunities plus reduce the loss. Okay, fine. So then this is typically done in the baseband. That's how it is done. Okay, so look at this. So you look at the baseband architecture. That's what I'm going to show you now. Okay, what is happening here? If you look at, this is how we have architected it. Okay, this is our own design. So what is happening here? This is the baseband. Okay, what is this? This is Xeon server. Okay, this is basically does the complete this RRC, PDCP, RLC MAC, 8086 server, right? And then after that, it is connected. It is passed on to this daughter card. It basically like contains a lot of FPGAs to do this physical layer processing. Fine. And what this does is basically sends this signal to the RF. And what this does is basically sends this signal to the, where is this connected? This is connected to the base, to the core network. Okay, once you have done all this processing, okay, right, this data goes to the core network. So this is the data which is going to the core network. Okay, that's how we have architected. Complete 8086 FPGAs, physical layer. On one side it is sent to the RF, on other side it is sent to the backhaul. Further below it up, this is the kind of processing which is happening in this. Two FPGAs, then these are the optical link which take it to the front hall. This is the PCI link which connects this baseband FPGA to the Xeon server, 8086 server. Okay, so complete this processing happens here over the PCI link. It is sent to the baseband, then it's sent to the RF. On the other side, it is sent to the backhaul. Okay, and this is how this system is designed. Okay, wherein there are two FPGAs. On one side PCI, this part. On the other side RF. Optical connection. It gives the signal to the RF. Fine. Okay. So this is I have shown you. This is what we have designed. Okay. This is a baseband card, and this is just a snapshot of it. And you fit them inside these on the motherboards. So these cards are going to sit inside the motherboards, and this is the chassis. Okay, that's how it happens. So you see this is how the baseband is designed. Go to the RF. Okay, so now you get this signal on the front hall to the RF. Okay, there's a massive antenna system. Okay, so take this without. So this is basically 64 antenna system. Okay, what these are called basically the daughter cards. Okay, they do. Each of them does processing for 16 antennas, so there are 4 of them, 64. And this is another card which sits inside this. Okay, this is called data aggregator card. Okay, right. So why do we have four such cards? Because each card can only handle processing for 16 antennas. Okay, and what it does is these cards process for 16 antennas. There is this data aggregator card which aggregates data from all these antennas and then sends it to the baseband unit over an optical link. On the other side, there are antennas. Okay, you see that's how it's architected. That's how it is. This is a radio, this is a baseband, and on the other side, this is the core network. Okay, optical link on one side, backhaul on the other side. Right, this is a radio. Done. Antennas. So one can design this radio. A company can design this radio. Another company can design the baseband unit, complete with the software, and they should talk to each other. They should be plug and play, right? Okay. Now, a user or an operator is not tied to one particular vendor. Okay, like Nokia's or Ericsson's. Somebody can do this, somebody can do that. So that with the competition, the cost of each one of that comes down. That's the ideal perspective. Okay, right? So this is the 5G network architecture. Okay, now we have some time. Okay, so what we are going to, so this is how we have architected it. Okay, what have we done here? We basically learned what kind of processing requirement each of this layer has. Okay, and then build a system to execute those layers. Okay, and if we start doing, just for example, okay, here if you use this, if you don't use this baseband card, and what you do here is I'll use this server for physical layer processing, you are going to run into problem. Okay, you are not going to stick to the timings, strict timings which the physical layer has, right? Okay, so you need to design a system like this, correct? Okay, then other part is basically the commercial part. wherein like you are splitting it. You can in principle do this processing here also, right? The low phi processing, which we basically segregated earlier, this could also be done here, okay? But again, the system costs are high. Who's going to buy that technology? Right? That's the philosophy of splitting that, doing that split at the physical layer. Okay, so that the cost comes down and users are benefited. Right? Okay. So I think this is typically how all other companies are also implementing, and that's how there is a common consensus. As I've told you, everybody understands that the like society has reached this stage, or the technology has reached this stage, that this needs to be done. Okay, and everybody does the same thing. Okay, right? So we'll stop here, and then we'll continue in the next class. Okay. Thank you.